In this recording, we are going to learn how to do a mix design using the American Concrete Institute method. There are 10 steps in ACI method. First is assemble required material information, select slump from table, select maximum aggregate site, estimation of water and their air content, select water to cement ratio from target strength table, calculate cement content from water to cement ratio, estimate coarse aggregate content, estimate of fine aggregate content, adjust for moisture content in aggregates, then we do a trial batch. Let's see in detail these steps. First step is assemble required material information. We need to know the raw material properties. We need to know the information on the structure, and also there are some other information sometimes we may need. When you look at the raw material properties, we need the sieve analysis data for the fine and coarse aggregates. That means the particle size distribution. We need to know the unit weight of coarse aggregates, bulk specific gravities of coarse aggregates, fine aggregates and the cement, and also the adsorption capacity of aggregates. These properties can be found by doing lab testing. Then we look at the information on the structure. We need to know the types and dimensions of the structural members, minimum space between the reinforcement bar, depth of slabs, required concrete strength and exposure conditions. There are other information as well we may need, like air content and other cementitious materials that may use in the concrete mix. After finding the material information, second step is to choose the slump. Slump is usually specified depending on the application. If not specified, we can use the table 10.1 to find the slump. As a general rule, the lower slump that will permit adequate placement should be selected. It is common to design a concrete for a lower slump and then increase it using water reducing admixtures. You can see the table 10.1 here. In that you can find the slump, minimum and the maximum value depending on the type of construction. For example, reinforced foundation walls and footings need a slump between 75 to 25 millimeters, plain footings 75 to 25 millimeters, beams and reinforced walls 100 to 25 millimeters, building columns 100 to 25 millimeters, pavement and slab 75 to 25, and mass concrete 50 to 25 millimeters. Third step is to select the maximum aggregate size. As a general rule, the largest maximum size of aggregates available should be used to minimize the required cement content. However, there are some limitations in reinforced concrete, as you can see in this table. Depending on the situation, we have to select the maximum aggregate size. For example, form dimensions, the maximum aggregate size should be 1/5 of minimum clear distance. Clear space between reinforcement or pre-stressing tenders, the maximum aggregate size should be 3/4 of minimum clear space. Clear space between reinforcement and forms, the maximum aggregate size should be 3/4 of minimum clear space. Unreinforced slabs, the maximum size of aggregate should be 1/3 of thickness. Larger size can be used in unreinforced mass concretes where limitations of size do not apply. Step 4 is estimation of mixing water and air content. Water content is related to the maximum aggregate size, workability and air entrainment. We can find this information from the table 10.2. We know the slump and we know the maximum size of aggregate, so we can use this table to find the water in kilograms per cubic meter of a concrete mix. Depending on whether we are making an un-air entrained concrete or air entrained concrete, we have to select the right part of the table. So top part is for non-air entrained concrete and the bottom part is for air entrained concrete. For example, let's take we have a slump of 80 to 100 and the maximum size of aggregate is 25 mils. To make an un-air entrained concrete, we need to have 195 kilograms of water. For the same slump, to make air entrained concrete, we need to have 175 kilograms of water for the same maximum size of aggregates. Also, we can use this table to find the approximate amount of air in the concrete. For non-air entrained concrete, for the same maximum size, we need to have 1.5% of air entrainment. For air entrained concrete, depending on the severity or the exposure, for example, if the concrete is exposed to sulfate, depending on that exposure, we need to select the right amount of air entrainment that we need to have. For mild exposure, we need to have 3% of air content for the same maximum size of aggregate. For moderate exposure, we need to have 4.5% of air entrainment. And for severe exposure, we need to have 6% of air entrainment. Step 5 is selection of water to cement ratio or the water to cementanious material ratio. Here we are considering few requirements and select the minimum water to cement ratio for the calculations. When we consider strength requirement, we refer the table 10.3. We know the compressive strength of our concrete, and depending on whether we are making air entrained or non-air entrained concrete, we select the water to cement ratio from the table 10.3. When we consider the durability requirement, maximum permissible water to cement ratio for different exposures you can find here. It depends on the type of structure as well. Considering all this, we can find the water to cement ratio from the table 10.4 as well. We can use table 10.5 again to find the water to cement ratio. So depending on the conditions of exposure and the minimum specified 28 days concrete strength, we can find the water to cement ratios here. They are the maximum values, and also we can use the table 10.7. Depending on the sulfate exposure, we can find the water to cement ratios here as well. So we have few water to cement ratios from 4 different tables. We select the minimum value to calculate the rest of the parameters. Step 6 is calculation of cement or cementanious material content. We already found the water to cement ratio. So using this equation, we can find the weight of cement. Many specifications also require a minimum cement content. Replacement of portion of cement by a mineral and mixture can be made on the basis of mass or volume. Step 7 is estimation of coarse aggregate content. For doing this, we need to know the dry rodded bulk density of coarse aggregates. Let's take the dry rodded bulk density of coarse aggregates as 1600 kilograms per meter cube as an example. So this is the dry condition and rodded bulk density. So from the table 10.8, we can find the volume of coarse aggregate per unit volume of concrete if we know the maximum size of aggregate and the fineness modulus of sand. For example, let's take that the maximum size of our aggregate is 25 mils and the fineness modulus is 2.6. Then we have 0.69 here, which is the volume of dry rodded coarse aggregates per unit volume of concrete. Now, if we times this 1600 by 0.69, we can find out the kilograms of coarse aggregates that we have in the concrete mix in the dry condition. To find the surface saturated dry condition, the weight of coarse aggregates in the surface saturated dry condition, what we need to do is we need to times this number by 1 plus the absorption capacity. So absorption capacity, for example, let's take 0.5%. So we times this number by this number, we get the coarse aggregates in surface saturated dry condition. Step 8 is estimation of fine aggregate content. There are two methods to do this, volume method and the mass method. Volume method is the preferred method. In this method, components, weight, and specific gravity are used to determine the volume of the water, coarse aggregates, and the cement these volumes plus the volume of air are subtracted from the unit volume of concrete to determine the volume of fine aggregates. Then we convert this volume to mass. As you see here, volume of fine aggregates will be the volume of the concrete mix, which is 1 cubic meter, minus the volume of cement, minus the volume of coarse aggregate, minus the volume of water, and minus the volume of air. So volume of concrete mix is 1 cubic meter, and we can find the volume of cement by dividing the weight of cement by the specific gravity of the cement. And the volume of coarse aggregates can be found by dividing the weight by the specific gravity of coarse aggregate. And we can find the volume of water by dividing the weight of water by the specific gravity, which is 1. And we minus the volume of air. Then we can convert this volume of fine aggregates to mass of fine aggregates using this equation. We times it by the bulk surface saturated dry specific gravity of fine aggregates, and we can find the amount of fine aggregates in kilograms in a cubic meter of concrete mix. To estimate the fine aggregate content using the mass method, we use the unit weight of fresh concrete. So we can find the unit weight of fresh concrete in the table 10.9. If we know the maximum size of aggregate, and if we know whether we are making non-air entrained concrete or air entrained concrete, we can find out the unit weight of fresh concrete from this table. For example, let's take the maximum size of aggregate is 25 mils and we are making non-air entrained concrete. So the unit weight of the fresh concrete is 2375. So that means this 2375 kilograms in a cubic meter of fresh concrete, this is the total weight, and we already found the weight of coarse aggregates, weight of water, and weight of cement. If we deduct all these three from the total weight of the fresh concrete, we can find the weight of fine aggregates. Step 9 is adjustment for moisture in the aggregate. The mix proportions determined by step 1 to 8 are assumed to be on the saturated surface dry condition. If aggregate contains free moisture, that means if aggregates are with more water than saturated surface dry condition, that additional water can contribute in the hydration process. So we have to reduce the mixing water content that we have calculated before, and we have to increase the amount of aggregates. If aggregate is air dried, that means aggregate has less water than saturated surface dry condition. So we need to increase the mixing water content which we have calculated before and reduce the aggregate amount correspondingly. Last step is trial batch. The purpose of making a trial batch is to verify the concrete mix meets design requirements prior to use in the construction. We determine the slump, cohesiveness, segregation tendency, unit weight, air content, and finishing in the fresh concrete, and strength in the hardened concrete. So we measure the 28-day strength, slump, and the segregation. If the workability is okay but the strength is not, we need to reduce the water to cement ratio, keep water content unaltered, increase cement, reduce aggregates. If slump is not okay but strength is okay, we increase cement, reduce aggregates. If slump is too low, we can increase water and cement content or use water reducing admixtures or superplasticizers. If slump is too high, we can reduce water and cement content or reduce the dosage of water reducing admixtures or superplasticizers. If segregation occurs, we can increase fine aggregate and reduce coarse aggregate accordingly, or else replace coarse aggregate with fine aggregates. We have discussed all 10 steps in ACI method of mix design. There is a numerical example in your tutorial. You can try it now.